Thank you, Dr. Hartmann, for meeting with us today. I really appreciate your time. Our first question for you is, what major updates have you made to the new edition of the book compared to the last edition?
So the previous version was black and white. This version, most of the figures have been improved and converted to color. And I added a new chapter. All the chapters are the same except for one. In the middle, I added a new chapter on natural variability of climate. I thought it was important to do that because it's important to know how natural variability is generated and that it may influence the structure or detection of climate change. A natural variability can mask or mimic temporal change like human-induced global warming, and we expect change to express itself first in the modes of natural variability. There's something called the fluctuation dissipation theorem that says that the first changes in the mean state of a system should look sort of like the natural modes of variability. So when thinking about climate change, you need to know about the structure of natural variability that the climate system exhibits. Things like stationary waves, annular modes, the Madden-Julian oscillation, El Nino Southern Oscillation, and the Pacific Decadal Oscillation are examples of low-frequency variability that can disguise or interact with actual climate change. Then the last chapter of the book, which is more the researchy part, has been completely updated to take into account new scientific discoveries and recent assessments made by the IPCC, for example. The timing of the book was pretty fortuitous, I think, because we finished with the fifth assessment of the IPCC in 2014, and I finished the book in 2015. So
Good time.
I was able to use the latest information.
So the second question we have is, what scientific developments were made in atmospheric sciences since the last edition that you implemented in the new edition?
So there's a lot more remote sensing data available. The modeling studies are much more detailed, both in terms of the spatial resolution, because the computers have gotten more powerful, and also because of the number of processes involved. Global climate models were pretty simple back in the 90s, and now they include many more processes related to chemistry, hydrology, etc. I think we understand the climate change much better now. The first edition was written before the definitive scientific work on detection and attribution of climate change was done. So now we know that the climate, for sure, that the climate is changing because of human activities, and that was still a little bit uncertain back in the early 90s. So much more work on climate feedbacks has also been done, and we know more about cloud feedback, and overall we have a much more definitive story on human-induced climate change, and our understanding of past climates like ice ages, that's also advanced quite a bit since the early 90s.
That's true. Great. Our third question is, how have technological advances influenced the way you have developed your new textbook?
So, yeah, when I wrote the first edition in 1993, desktop publishing was rather new. I think I used a Mac Plus or something that looked like a Mac Plus, and the chapters were each individually on a 3.5-inch floppy disk.
Nice.
So that was a while ago. Figures were often made by drawing on paper by an artist or a draftsperson. Today, one person working alone, like myself, can download a data set in a self-describing format like NetCDF, pull the data into a high-level programming language like MATLAB or Python, and produce a publication-quality color figure in one day from start to finish. Right? So I made most of the original figures in the second edition myself. Back in the 1990s, professors had much more human help. We had staff people to do things. Now we do almost everything ourselves, usually using computers or the web. So bookkeeping, typing letters, mailing stuff, we do that all ourselves now. 20 years ago, there were people around to do that. That's right.
Interesting.
So our fourth question is, we were talking to Dargan, and we were talking about the the term annular mode that you're known for coming up with, and we were kind of wondering what discovery or observation led you to this term.
Okay. So Mike Wallace and his students were using terms like Arctic oscillation and Antarctic oscillation because there was a large surface pressure variation over the pole and a variation of the opposite sign more or less around that. But the poles actually encompass a small area, and we discovered that what drives the variations in these structures in the atmosphere is the interaction between mid-latitude eddies and the east-west elongated jet streams in mid-latitude. So focusing on the Arctic or the Antarctic seemed like it was drawing attention to the wrong thing. The action's really in the north-south shifts of the mid-latitude jet streams. The long periods and persistence times of these shifts is related to an eddy-jet feedback. The jet moves around, the eddies move with it and sustain it in the new position against surface friction or whatever is trying to relax the anomaly back to the climatology. So that jet feedback sustains the jet shifts for much longer periods of time, much longer than the frictional decay time of wind anomalies, and that sort of dynamics is essential to understand things. In the southern hemisphere, especially in the summer, the mid-latitude eddy-driven jet extends almost all the way around the Earth from east to west, so that it shows up very well in a zonal average and looks like an annulus or a donut in a polar projection map. Therefore, the southern annular mode seems like a better name than the Antarctic oscillation, since the action is not really in the Antarctic but over the southern oceans where the jet stream is. Still, annular may not be the best term either, since jets need not go all the way around the Earth for the feedback to work. For the eddy feedback to work, the jet just has to be long enough relative to the scale of the eddies so that a baroclinic eddy in mid-latitudes can experience its full life cycle within the jet and then interact with the jet. So a banana-shaped jet is good enough, but banana mode doesn't sound as sophisticated as annular mode. So a localized jet still has the ability to remain relatively stationary through its Rossby wave dynamics. And we also began to refer to the extratropical jet as the eddy-driven jet to distinguish it from the subtropical jet, which mostly results from angular momentum conservation in the Hadley circulation. Have you got to that yet in
Yes, sir.
in dynamics?
Yep.
Okay, good. That's all.
Great. Our last question is, how is writing an IPCC report different from writing your textbook?
Okay, so both are really summaries of what is known. In the case of a textbook, your audience are students who want to learn. In the case of the IPCC, it's an assessment of the current state of science with an emphasis on what has been learned recently. The audience for the IPCC assessment is other scientists, the public, and policymakers. In a textbook, you can write pretty much what you want without asking anyone else's opinion. Then you wait to see the reviews after it's published, all right? You can choose to have co-authors in a textbook, or you can write every word yourself. For the IPCC leadership recruits a committee of scientists, and they write several drafts. Each draft is heavily reviewed by a wide range of people, from eccentrics to scientific experts to politicians. The authors of the IPCC reports have to respond to every question before the report is published, and there's a permanent record of that. An executive summary, a much shorter document for policymakers, is written, and for this document, every line has to be approved by a set of representatives that governments send to a meeting where this review of the executive summary for policymakers is reviewed. Scientists are there to make sure that the final document is consistent with what is understood about science at the time the report is written. So some representatives from some country might want to change the words, but if they want to change the words in such a way that it becomes inconsistent with what we know about the science, then it doesn't happen. So it's good
Okay.
that science has some primacy in that process, right? So IPCC reports have press releases and get a lot of attention. Textbooks can have an impact, but usually in much more subtle ways, right?
It's true.
Okay. That's it.
Awesome. Thank you so much for your time, Dr. Hartmann. Really appreciate it.
You're welcome.
Thanks a lot.
Sorry for reading it, but I wanted to squeeze all that in without hemming and hawing too
That's
much.
all good. What got you into weather and atmospheric science? Like, were you just always fascinated
No,
by
not
as a
at
kid?
all. I was an undergraduate major in mechanical engineering,
Really? Okay.
and I was really interested in fluid dynamics, aerodynamics. So I applied to a lot of schools that had really good aerodynamics problem and programs. And one of them sent me a brochure about a geophysical fluid dynamics program.
Like, interesting.
I was young. I said, okay, I'll do that.
Nice.
It's really cool.
That sparked it. Cool.
That's awesome.
Kind of cool to hear that story.